Okay, time for another physics presentation. I'm going to try this one without my face. Let's see if you like this one better or worse. Let me know in class whether it's better with my face or without. No offense taken. All right, today we're going to be talking about Newton's laws. Here's a depiction of Newton sitting under an apple tree. You may know the significance of that. Newton was an interesting character. Here I picture two Isaac Newtons. These are from drawings from his lifetime. They looks very different. I guess this was a younger picture and an older picture. And in the picture on the right, I think he kind of looks a little bit like the guitar player from Aerosmith. Joe Perry. So, I don't know, what do you think? Does he kind of look like Joe Perry in that picture? If you don't know who Joe Perry is, then here's a side-by-side. I think they kind of look similar there. What do you think? Well, at any rate, Isaac Newton, interesting character, of course, and we are going to now be talking about what they call Newton's laws. Now, I do want to point out with Newton's laws that they were all written down by Galileo before Newton was born. Newton did not take credit for what we now call Newton's laws. He did say that if he has seen farther, it's by standing on the shoulders of giants. Nice things about human beings. We can take what's done from the generation before and build on it, and Newton certainly built on what Galileo did. But just an interesting historical footnote that what we call Newton's laws, Galileo had already come up with before Newton was born. But we'll proceed to call them Newton's laws as is the custom of our times. Okay, so today we do talk about Newton's laws or Galileo's laws. We agree with them. They were very different than the way the ancient Greeks used to look at motion. And they had laws that they had come up with. And again, they were kind of made very good sense, but we now look at them a little bit different, and it's Galileo and then Newton who helped us to see them a little bit different. But pretty good things that they came up with, and since we sort of build on their foundation, we'll talk about it a little bit. In Newton's, the Greeks' way of looking at things with motion, they talked about anything falling through the air as natural motion. Things were naturally falling because they had a hierarchy on the earth. And the hierarchy that they understood was that earth was the lowest, and then there was water, and then there was air, and then there was fire. So anything moving in the air, they described as natural motion, trying to get to its natural place. Rain would fall through the air, but it would collect on top of the ground because it was above the earth. And a rock would fall through water if you let it, because it was trying to get to its natural position. Interesting way of looking at things. No forces were recognized here. Already, you're probably thinking, well, no, it's gravity that causes that motion. They didn't have that figured out yet. It took Galileo and Newton to come up with that concept. So they explained this as the natural hierarchy of things, and they also felt that an object's natural position was at rest, including the Earth itself. Okay, so Newton's first law of inertia, we should talk about what inertia is. Inertia is a resistance to change. So Newton's first law really starts out like the ancient Greeks. An object will continue at rest if that's what it's doing, as if that's its natural state. But here's the other part. It will continue in a straight line at a constant speed unless you make it do otherwise, meaning that there has to be a force involved to make something change what it's doing. Up until now, we've been talking about kinematics, a description of motion, and now we enter what they call dynamics, and that is a explanation of motion, why it happens, not just a description. Okay, and of course, the reason that the motion happens is forces. Somebody told me once a long time ago that all of physics is broken down to pushes and pulls, and really it does come down to those forces. So now there are forces that we can talk about when describing motions. Things don't slow down because they want to come to a rest. Friction compels them to. And falling objects are falling because of gravity, not because it's their natural position to do so. And that's a new view of motion. So now we can talk about the amount of inertia. If inertia is a resistance to change, then the more mass you have, the more you are resistance to change. So mass is going to be a way of measuring inertia, the amount of inertia that you have. Okay, and we are going to measure mass in kilograms, and mass is often confused with weight. Weight and mass are not the same thing. Mass is the amount of substance that you have, and 1 kilogram of mass weighs 9.8 newtons. Interestingly enough, back to the apple, 1 newton weighs about as much as an average size apple. So that kind of ties it back into the newton a little bit. But 1 kilogram of mass has 9.8 newtons worth of weight to it. So kilograms is the unit for mass, and newtons is the unit for weight, and really for all forces. But weight is a downward force due to gravity. Mass is the amount of substance that you have. Okay, so for weight, that's the newton. This is a derived unit. Weight, mass, and gravity are involved in calculating, mass and gravity are involved in calculating weight, and there's your formula for it. You take your mass multiplied by the acceleration due to gravity. So weight, W is the weight, M is the mass in kilograms, and G, the acceleration due to gravity, which we've already discussed, is 9.8 meters per second squared at the sea level on Earth. So this is stuff that we're familiar with G, the acceleration due to gravity. We're now tying it into our new concept of weight. Okay, so unless we otherwise look at it, we're going to be on sea level at Earth. So what is the weight of a 1 kilogram object? Well, we've already talked about it, but here would be the calculation where you just plug it in. And again, this shows how the newton is derived out of the kilogram, meter, and the second. So a derived unit, which we've discussed earlier, and we are now discussing again. Okay, so how about it? What forces are acting on an object that's at rest? What do you think? Well, maybe pause and come up with your answer, but let's see. One thing is, if you're back now, weight. Weight is always going to be acting on an object. Objects are never really weightless. They may appear weightless, but they have a weight, a force due to gravity acting on them at all times. But think of an object sitting on a surface, an object at rest. It can't just be the weight pushing down. The thing would go right through the surface, right through the table, or right through the floor. So we talk about the normal force, also like a supporting force, a normal force that's also involved. And they don't call it normal because there is an abnormal force out there. Normal in the mathematics sense of perpendicular. So the normal force is a force that is perpendicular to the surface. So if we had the tire as pictured here, and it was just sitting there at rest, the normal force and the weight would be equal and in opposite directions. And here you see we're using arrows, and you can probably see that we're going to be getting back to a little bit of a vector conversation here. Okay, important now to talk about the idea of net force. Net force is going to be the balancing out of all the forces. This is going to be the total of all the forces. Really, for us, we could talk about it as a vector sum in any one direction. And we've been talking about vector sums already. So we could think about it in terms of a vector sum. It's going to be the total of all the forces in any direction. And this term here, sigma, is a term that means the sum of. So this is a way of talking about the net force if we talked about the sigma of all the forces. Okay, so let's see, a really straightforward example here. If you had some kids pulling on a tug of war here and there was 1,200 newtons to the left and 1,000 newtons to the right, well, what's the sigma? What is the net of the forces? You've probably got it already, but did you know that this was a famous tug of war? In fact, it lasted for about 25 years. Yeah. There's the same people later trying to win that tug of war. In the end, it was 200 newtons to the left was the answer. And hopefully you got that answer as well. Okay, so forces can be added as vectors, as I already mentioned. And a diagram that's used to show these forces is called a free body diagram. So here's a free body diagram that we might talk about. You can see the vectors there pushing down, the weight pushing down, the normal force pushing up. doesn't really matter exactly where you put the weight or the normal force. It's the direction of the arrow that's important. You'll see this in a later example. Here I'm also showing a box that maybe somebody's pushing across the floor of a warehouse or something. So there's an applied force pushing it, and then there's a force of friction working against it. We're going to start off without friction, and later on we'll build in friction calculations. In the beginning we'll work with friction without calculations. Okay, so free body diagrams could be used for lots of different things, and they get pretty complicated pretty quickly. You're going to do a problem with a helicopter here that's going to get a little bit complicated. But just to give you an idea of these free body diagrams that could be used, identifying the forces can be pretty valuable in understanding motions, and then again, what will happen because of those motions. The causes of the motions are understood, then you can understand and predict the motion that will happen. Okay, equilibrium. There's an interesting question. Equilibrium is when all the forces are balanced out. You're at zero. So here's an interesting question for you. Can an object be at equilibrium and still be moving? Why don't you pause and think about that? Well, what'd you come up with? Here's my answer. The answer is yes. Think about Newton's laws there. If the forces are balanced and there's no unbalanced force, an object will keep doing exactly what it was doing, moving at the same speed and in the same direction. Okay, and if the forces come out of balance, that's when they're going to slow down, speed up, or change direction. Like the young players on the air hockey table there. That puck is constantly becoming unbalanced in its forces. Okay, so let's see. Well, we've already kind of done this, so I'll breeze through this. If you were pushing a box to the right, what would the free body diagram look like? If we did take friction into account, we would have the normal force going up, the weight pushing down, we'd have the applied force pushing it to the right, and then the force of friction working against it. Very important to label all these forces. Okay, well that's nice on a flat surface. Things do change up a little on an incline. So here I have a box on an incline, and I have drawn in a force for the weight. But the weight is now going to be distributed differently because it is on the incline. So I want to give you an idea of how the force of gravity will be different and the normal force will be different when an object is on an incline. Okay, so let's see. Here, adding in a little bit more, I've drawn in my normal force. So there's my force normal, perpendicular to the surface. And I've also extended that normal force to go down to where my weight line is as well. So you can see my normal force has been extended over here down to where the weight line is also. I'm doing that because I want to show you that there is also a component of the force here, of this weight, that works right parallel to the surface. And that's the force that's really pulling the box down the incline, or working against you if you're trying to push it up an incline. You know that it's easier to push something up a ramp than it is to lift something directly. And this sort of gives you an explanation of why. It's because the weight is distributed a little differently on the incline. Notice here, because I've got a 90-degree angle in here, and I've got a 90-degree angle here with my incline, that this angle here is also the angle of the incline. And that lets me say that the component that's parallel, remember that parallel component that I mentioned? That'll be mg, the weight, multiplied by the sine of the angle. So it'll be less than the full weight of the object. Similarly, the normal force is going to be related to the cosine of the angle, or the weight multiplied by the cosine of the angle, as I've indicated here. And that means we have a way of showing the force that's pulling downward on the box, the force due to gravity, and it also gives us a way of talking about the normal force on an incline. This will become very important to us later on with problems that we're going to be solving. Okay, this brings us to Newton's second law. So Newton's second law is really the basis of this. On the surface, a very straightforward equation. However, it gets complicated quickly with the type of problems that are involved, especially once we throw friction in, which we'll leave for another presentation. Okay, so Newton's second law talks about the force and acceleration, and it should make sense a little bit here. We've talked about the idea that to cause something to change what it's doing would be an unbalanced force. So if you cause something to change speed or to change direction, you are causing an acceleration. So even a direction, if you think about velocity, even if you kept the same speed but your direction changed, that means your velocity would change, which means that you would have an acceleration. And it takes an unbalanced force to cause an acceleration. So here we go. This should make some pretty good sense here, is that the acceleration is going to be directly related to the force and inversely related to the mass. What am I saying there? Well, here in the simplest form is Newton's second law, meaning if I double the force, I double the acceleration if I keep the mass the same. And if I increase the mass, I'll have to double the force to get the same acceleration, or I could say the acceleration would be half as much if I doubled the mass. And that's really what we're saying here. And let's say it again, the F is the net force, and the M is the mass, and the A is going to be the acceleration. So there basically is Newton's second law, F is equal to ma. However, on your formula sheet, they're going to give it to you a little bit differently, and this is the way it's going to appear on your formula sheet, where the sum of the forces divided by the mass is equal to the acceleration. And that's what you're going to see on the formula sheet. It's really taking F is equal to ma, jumbling it around a little bit to be in terms of acceleration, and also owning up to the fact here that it's the net force. It's the sum of all the forces. This is also with the arrow above it showing that it is a vector quantity. So you have to remember that these forces that you're dealing with are going to be in one dimension at a time. Maybe the forces in the x direction or the forces in the y direction rather than both. Okay, here is an example that is going to help me to illustrate that to you. And then I believe you'll be able to get started on some problems. All right, so let's take this scenario of a person pushing a 20-kilogram lawnmower. Let's picture a lawnmower here, an old style one that doesn't have something that helps you move it along. The wheels don't spin. You got to do all your pushing by yourself here. So here I'm asking for the normal force and the acceleration, and it lets me demonstrate some of these Newton's laws concepts. Okay. So here's my free body diagram that I'm starting off with, and what I am doing there is I'm labeling the force that's being used, and that box there is my lawnmower. I'm not very good at artistic endeavors when it comes to drawing. But you can picture that box as the lawnmower, and that's the downward force pushing on it. Well, it's at an angle of 50 degrees, so I add that in as well, and I'm kind of getting a good idea of the forces. I also have the weight pushing down, so I'll add that in there. There's my mg, showing the weight pushing down. Okay, so now I'm also going to add in here the normal force pushing upwards, and really the force pushing downward, the F, the normal force, and the weight, those are the only three real forces. But I am also here splitting my force into the components in the x direction and the y direction. Okay, well, why am I doing this? Well, I'm getting started on my problem here, and my diagram, I believe, will help me. I'm also going to now indicate what I know already, that the F in the diagram is 70 newtons, and the mass is 20 kilograms. Okay, one step further here, I'm showing that the force in the y direction is going to be that 70, which is the hypotenuse of my right triangle over here, multiplied by the sine of 50 degrees since it's the opposite side. So I have 54 newtons over here in the force in the y direction, pushing down in the y direction. Also, with the weight of a mass of 20 kilograms, I have 196 newtons pushing down. The normal force is the force that the surface has to use to counteract all the downward forces. So here I'm showing that the normal force is going to be that force in the y direction plus this weight pushing downward, which gives me a force of 250 newtons. You see how I'm adding all of these forces? I'm getting the sums of the forces together here, and I'm doing that in the vertical direction. I'm also making them equal, if you didn't pick up on that, because there is no unbalanced force. The normal force reacts to and balances out these two downward forces. So they are equal. In a way, I could say that my sum of my forces in the y direction is 0. And I would be entirely correct in saying that. Now, in the horizontal direction, I do have an unbalanced force, and that unbalanced force will cause the acceleration. So here I'm showing that. The force in the x direction is going to be using the cosine of the angle. It's the adjacent side over here. So the force in the x direction is 45 newtons. And using my formula, my version of Newton's second law here, there is my acceleration, my 2.3 meters per second squared. Well, how did you do with that? That's a pretty good start for Newton's laws, and it'll certainly let you solve or give you a good chance at solving the problems that I'm putting in front of you. Well, I hope that was okay, and I hope you enjoyed that. And if you have any questions, please bring them to class. I look forward to seeing you there.